Here's a breakdown of the general process. 1. Rubber extraction, natural rubber. Tapping. Natural rubber is derived from the latex of rubber trees' heavy abrasives. Workers tap the tree by making incisions in the bark, allowing the latex sap to drip out and collect in containers. Collection. The collected latex is transported to the factory for processing. The latex is often diluted with water to reduce its viscosity. 2. Coagulation, natural rubber processing. Coagulation. The latex is treated with acids like formic acid to help it coagulate or solidify. This process turns the liquid latex into a more solid, rubbery form. Centrifugation optional. Sometimes, the latex undergoes centrifugation to separate the liquid from solid rubber particles, improving the consistency. 3. Mixing and compounding. Blending with additives. The rubber is then mixed with various ingredients to enhance its properties. Common additives include vulcanizing agents like sulfur to improve elasticity, plasticizers to make the rubber more pliable, carbon black to reinforce the rubber and increase durability, antioxidants to prevent degradation over time, processing oils to help with molding and improve workability. This mixture is done in large industrial mixers known as Banbury mixers or internal mixers. 4. Vulcanization curing. Vulcanization. This step is crucial in transforming raw rubber into a durable, elastic material. The rubber is heated with sulfur or other curing agents to cross-link the polymer chains. This process gives the rubber its strength, elasticity, and heat resistance. Molding or extrusion. The vulcanized rubber is either molded into specific shapes or extruded through machines to form long, continuous sheets or tubes. Common products like tires, seals, gaskets, and hoses are made this way. 5. Shaping and molding. Molding. In the molding process, the rubber is placed in a mold that shapes it into its final form. This could be anything from a tire to rubber bands or industrial components. Extrusion. For products that require continuous shapes like hoses, gaskets, or seals, the rubber is pushed through an extruder, where it's shaped into the required cross-section. 6. Finishing. Cutting and trimming. After the rubber is shaped, it's trimmed to the correct size and shape. Testing. Quality control tests are performed, including tensile strength, elasticity, and durability tests, to ensure the product meets the required specifications. 7. Packaging. The final rubber products are packaged, either for direct shipment to customers or for further processing if necessary. 8. Recycling optional. Some factories also recycle scrap rubber and waste material, either by reprocessing it into new products, or by using it as fuel and energy generation. 1. Rubber extraction, natural rubber. Latex harvesting. Rubber tapping is a delicate process. The latex, which is a milky fluid, is harvested early in the morning when the latex flow is at its highest. The quality of latex can vary depending on the age of the tree, weather, and other environmental factors. Transportation to the factory. Once collected, the latex is transported to processing facilities. During transportation, the latex is sometimes preserved by adding ammonia to prevent premature coagulation. 2. Coagulation, natural rubber processing. Acid coagulation. When the latex reaches the factory, it's treated with acids, like formic acid or acetic acid, which cause the rubber particles to clump together and form a solid mass. Alternative coagulation methods. Some factories use more modern techniques, such as enzymatic coagulation, where specific enzymes break down the proteins in latex to speed up the coagulation process. This is a cleaner method compared to traditional acid coagulation. 3. Mixing and compounding. Precision mixing. In this stage, precise formulas are used to ensure the rubber has the desired characteristics. Compounding is an intricate process because the balance of ingredients will affect the final product's performance. The types and amounts of chemicals added will determine the rubber's hardness, strength, flexibility, and other qualities. Types of mixers. Banbury mixers. These are heavy-duty machines with an internal rotor that mixes ingredients under high shear. This intense process makes sure that the rubber is fully blended with additives. Tool mills. These are simpler machines used for mixing smaller batches of rubber. The rubber passes between two rollers that work the ingredients into a smooth blend. For vulcanization, curing. Vulcanization process. When the rubber is heated, the sulfur molecules form crosslinks between the polymer chains, making the rubber more durable and elastic. The temperature and time in the vulcanization process depend on the thickness of the rubber and the type of product being made. Different vulcanization methods. Hot vulcanization, the traditional method, where rubber is heated in molds or continuous processes at high temperatures, up to 170 degrees Celsius or 338 degrees Fahrenheit. Cold vulcanization. This involves using peroxide-based curing agents and requires lower temperatures, about 120 degrees Celsius or 248 degrees Fahrenheit, and it's often used for certain specialty rubber products. Vulcanizing agents. The most common agent is sulfur, but alternative cross-linking agents such as peroxides are used for specific products, especially in high-performance materials. 5. Shaping and molding. Compression molding. For products like seals and gaskets, rubber is placed in a mold cavity and compressed to fit the shape. This process requires precise control of time and temperature for the perfect mold. Injection molding. In this method, rubber is injected into molds using pressure, which allows for more intricate designs, especially for small or detailed components like rubber parts for electronics. Transfer molding, a hybrid of compression and injection molding, where rubber is placed into a chamber and forced into the mold under heat and pressure. 6. Finishing, curing and post-curing. Some rubber products require additional curing after the initial vulcanization. This process, known as post-curing, helps complete the chemical reactions, enhancing the final properties of the rubber. Surface treatment. Depending on the application, the surface of rubber products may be treated to improve its properties. For example, tires are treated with a thin layer of anti-ozone wax to protect them from cracking. 7. Testing and quality control. Physical testing. Rubber manufacturers test the final products for mechanical properties such as tensile strength, elongation, hardness shore A or D, compression set how much the rubber deforms under pressure, and tear resistance. Non-destructive testing NDT for critical applications, for example, rubber components for aerospace or automotive. Non-destructive testing methods such as ultrasonic inspection or X-ray inspection are used to ensure the rubber product is free from defects. 8. Packaging and distribution. Final products. Rubber products are packaged in bulk or as individual units, depending on the customer. Finished goods like rubber hoses, seals, gaskets, and tires are typically packaged for distribution. Customization. Some rubber factories provide customization options for their customers, allowing for the creation of specific blends, colors, or sizes of rubber products to meet specialized needs. 9. Synthetic rubber production alternative to natural rubber. Types of synthetic rubber. Unlike natural rubber, synthetic rubber is made from petrochemical derivatives. Common types of synthetic rubber include SBR styrene butadiene rubber, used in tire manufacturing, EPDM, ethylene propylene diene monomer, common in automotive and weather-resistant applications. NBR nitrile rubber, known for its resistance to oil, fuel, and chemicals. Polymerization process. Synthetic rubber is produced through polymerization, where monomers, for example, styrene butadiene, are chemically bonded together to form polymer chains. This is done through a controlled process involving initiators and catalysts. 10. Recycling and sustainability. Rubber recycling. Rubber waste, especially from tire production, is a significant concern. Some factories implement recycling processes to reuse scrap rubber for other products, like mats, playground surfaces, or even as fuel for energy generation. Sustainable materials. There's growing interest in bio-based rubbers, like guayal rubber or dandelion rubber, which aim to reduce reliance on traditional rubber plantations and petroleum-based synthetic rubbers. Research into biodegradable rubber is also underway. 11. Advanced manufacturing techniques. 3D printing. With advances in additive manufacturing, some rubber products are now being made using 3D printing technology. This allows for rapid prototyping and custom designs without the need for traditional molds. Nanotechnology. Some advanced rubber products incorporate nanoparticles, for example, carbon nanotubes, to enhance properties like strength, conductivity, and wear resistance. 12. Rubber recycling and sustainability continued. Tire recycling. One of the major sources of rubber waste is old tires. Recycling tires is an environmentally complex process, but there are several ways to repurpose the material. Crumb rubber. Tires are shredded into small pieces, crumb rubber, which can be used in the production of new rubber products, playground surfaces, rubberized asphalt for roads, and even as fillers in various rubber products. Pyrolysis. Tires can be heated in the absence of oxygen, a process called pyrolysis, to break them down into useful byproducts like oil, gas, and carbon black, which can be reused in industrial applications. Biodegradable rubber. There is ongoing research into developing biodegradable rubbers that can break down naturally, reducing the environmental impact. Materials such as rubber made from plant-based sources, for example, guaiacol and dandelion, are being explored as alternatives to traditional synthetic rubbers. Rubber waste to energy. Some factories use rubber waste as an alternative fuel for energy production. This is particularly relevant in regions where energy costs are high and waste management is a challenge. Rubber waste can be burned in specialized furnaces that extract energy, reducing landfill waste. 13. Emerging trends and technologies in rubber manufacturing. Smart rubber. The rise of smart or intelligent rubber materials is a growing trend in high-tech applications. These rubber materials incorporate sensors or conductive materials to make them capable of monitoring environmental conditions. For instance, self-healing rubber, a breakthrough technology that allows rubber products like tires to repair themselves if damaged. This is achieved through incorporating microcapsules filled with healing agents that are released when the rubber is punctured. Conductive rubber. Rubber products embedded with conductive fillers such as carbon nanotubes or graphite. This type of rubber can be used in applications such as wearable electronics, anti-static materials, and even sensors. Rubber foam and lightweight materials. Another area of development is the creation of foamed rubber, which is lightweight and often used in packaging, automotive interiors, and insulation. Foamed rubber products are made by incorporating air bubbles into the material, which reduces weight and enhances cushioning properties. 14. Rubber for special applications. Rubber isn't just used for tires, seals, and gaskets. It has a wide range of specialized applications, and manufacturers tailor the properties for specific needs. Automotive industry. Sealing systems, rubber seals, gaskets, and O-rings are vital to keep vehicles air and watertight. Sound dampening. Rubber is used in automotive parts to minimize road noise and vibrations inside the cabin. Medical industry. Rubber is used in many healthcare applications. Medical gloves. Latex or synthetic rubber is commonly used in disposable gloves for medical and laboratory purposes due to its elasticity and barrier properties. Tubing and catheters. Medical-grade rubber materials are used in flexible tubes and catheters, particularly in surgical and diagnostic procedures. Dental materials. Rubber compounds are used in dental materials such as impression materials and orthodontic footwear. Rubber is integral to footwear production, particularly in the making of soles for shoes. Different formulations are used for varying degrees of flexibility, durability, and comfort. Sporting goods. From soccer balls to tennis shoes, rubber plays a significant role in many sporting goods. Rubber provides grip, elasticity, and durability in a variety of sports equipment, including tennis balls. The core of tennis balls is made from rubber, providing the bounce and durability required for play. Athletic footwear. Rubber outsoles on sports shoes offer traction, durability, and flexibility. 15. Nanotechnology and rubber. Nanomaterials such as nanoparticles of carbon black, silica, or graphene are increasingly being added to rubber to enhance its properties. These materials help improve strength, wear resistance, thermal stability, and even conductivity in rubber. Graphene rubber. Graphene-based rubber is being developed for its incredible strength, conductivity, and elasticity. It's used in high-performance applications, including advanced electronics and specialized engineering. Laser and plasma surface treatments. Some rubber products undergo treatments like laser engraving or plasma surface modification to enhance their durability, adhesion, or wear resistance. These treatments help improve the bond between rubber and other materials in composite structures, such as rubber metal parts. 16. Rubber in the circular economy. Circular economy models. Rubber manufacturers are beginning to incorporate more sustainable, circular business models where the product life cycle is extended through repair, reuse, and recycling. For example, recycled rubber products. Some companies are focusing on creating new products made entirely from recycled rubber, such as playground surfaces, park benches, and tiles. This reduces the demand for virgin materials. Closed-loop systems. In a closed-loop system, the factory's waste products are reused in production. For example, Scrap rubber from one part of the process is fed into another part of the system to create new products. 17. Global challenges and future of rubber manufacturing. Environmental impact. The rubber industry is increasingly facing pressure to reduce its environmental footprint, both in terms of energy use and waste generation. This has led to innovations in sustainable practices, including the development of biodegradable rubbers and eco-friendly vulcanization methods. Deforestation and ethical sourcing. As rubber production relies heavily on natural rubber from rubber tree plantations, deforestation and unethical land use practices are major concerns. Companies are now looking to ensure that the rubber they use is ethically sourced, with many working to implement sustainability certifications like the Forest Stewardship Council (FSC) for rubber plantations. Synthetic rubber production and oil dependence. The growing need for synthetic rubber, which is derived from petrochemicals, raises concerns about its environmental impact. The industry is investing in renewable alternatives, like bio-based rubbers, to decrease reliance on fossil fuels. 18. Automation and robotics in rubber manufacturing. Automated production lines. Advanced factories are adopting automation in many parts of the rubber production process. AI and machine learning. Artificial intelligence. AI is being implemented in rubber factories for predictive maintenance, quality control, and even process optimization. AI algorithms help identify inefficiencies in production lines and can forecast potential failures in machinery, reducing downtime. 19. High performance and specialty rubber materials. Rubber is tailored for very specific applications, and manufacturers have developed advanced formulations for various high-performance needs. Here are some examples. Silicone rubber. Silicone rubber has unique properties, such as excellent temperature stability. It can withstand both high and low temperatures, electrical insulation, and resistance to UV degradation. Consumer goods, including kitchenware, electrical insulators, and seals in electronic devices. Automotive, for gaskets, seals, and high-temperature applications. They are widely used in industries such as aerospace, for seals and gaskets in engines, hydraulic systems, and fuel systems, where extreme temperature and chemical resistance is required. Chemical processing, for equipment that comes into contact with aggressive chemicals. Polyurethane rubber. It's used in industrial rollers, in heavy-duty machinery that requires long-lasting wear-resistant components. Tires. In some cases, for specialized tire applications requiring high durability, such as in construction vehicles or high-performance off-road vehicles. Butyl rubber, known for its excellent air retention properties. Butyl rubber is commonly used for tires, inner tubes and tubeless tire linings, particularly in high-performance tires. Pharmaceutical packaging, rubber stoppers and seals for vials and syringes. 20. Emerging materials and bio-based alternatives. Guayal rubber. Guayal is a shrub that produces a natural rubber that's becoming more popular due to its eco-friendly attributes. Guayal rubber is a potential alternative to traditional hevea rubber trees, which are often grown in monoculture plantations and face challenges such as deforestation. Guayal is also hypoallergenic, making it suitable for medical applications such as latex-free gloves. Dandelion rubber. The dandelion plant has been researched as a potential alternative source for natural rubber. The roots of the plant contain latex that can be extracted and processed in similar ways to traditional rubber. This could offer a more sustainable and local source of rubber, reducing reliance on tropical rubber plantations. Bio-based, synthetic rubber. Researchers are investigating the production of synthetic rubber from renewable sources like sugar cane, corn, or algae. Additive manufacturing. 3D printing with rubber. 3D printing with rubber filaments. The integration of rubber-like materials in 3D printing is revolutionizing rapid prototyping and small-scale production. These flexible, rubber-like filaments are made from thermoplastic elastomers (TPE) or thermoplastic polyurethane (TPU), which mimic the properties of rubber while being compatible with 3D printers. Rapid prototyping. Designers and engineers can create prototypes with rubber-like materials quickly and test them before moving to mass production. This is especially useful in industries like automotive, medical devices, and footwear. Customization. 3D printing allows for highly customized rubber parts to be made with unique designs, optimized for specific applications, or even tailored to individual consumer needs. 22. Advanced quality control in rubber manufacturing. As rubber products become more specialized, quality control processes have become more sophisticated. Some advanced techniques include Non-destructive testing (NDT). NDT methods such as ultrasonic testing, infrared thermography, and X-ray inspection are used to identify defects without damaging the product. These techniques are especially important for high-performance rubber products, such as those used in aerospace and medical devices, where reliability is critical. Spectroscopic analysis. This is used to analyze the chemical composition of rubber materials. Techniques like Fourier transform, infrared FTI or spectroscopy, or Raman spectroscopy allow manufacturers to verify the quality of the rubber compound by identifying chemical structures and verifying the concentration of key additives. This technique measures the flow properties of rubber compounds. By studying how the material flows under various conditions, manufacturers can adjust the formulation to achieve the desired processing characteristics and end-use performance. 23. Rubber in the automotive industry expanded. Electric vehicle tires. As electric vehicles (EVs) become more widespread, the demand for specialized tires increases. EVs require tires that are optimized for different factors compared to traditional vehicles, such as low rolling resistance. To maximize energy efficiency and driving range, tires are designed to minimize energy loss. Heavy loads. Electric vehicles often weigh more due to the large batteries, so tires need to be stronger and more durable. Noise reduction. Electric vehicles are quieter than traditional vehicles, so tires are engineered to reduce road noise and vibration. Tire performance under extreme conditions. High-performance tires, made of advanced rubber compounds, are being designed to withstand extreme temperatures, both hot and cold. This is particularly important for vehicles used in racing or high-performance sports. Rubber components in autonomous vehicles. As autonomous vehicles become more advanced, rubber parts are integrated into sensor housings, gaskets, and other components to ensure optimal function in dynamic environments. Rubber's ability to absorb vibrations is crucial for precision sensors used in autonomous driving technologies. 24. Rubber in the aerospace industry. Seals and gaskets. Rubber plays a crucial role in sealing systems used in aerospace applications. Seals made from materials such as silicone rubber or fluoroelastomers are used to prevent the entry of air, water, and contaminants into sensitive components like engines, fuel systems, and cockpit instrumentation. Vibration dampening. Rubber components are used to absorb vibrations in aerospace applications, particularly in engines and other mechanical systems. Rubber isolators help reduce noise and improve the comfort of the cabin. Heat resistance. Rubber materials used in aerospace need to withstand extreme temperatures, ranging from the sub-zero conditions at high altitudes to the intense heat during re-entry into the atmosphere. Specialized rubbers like silicones and fluoropolymers are selected for their thermal stability. 25. Rubber in environmental applications. Water filtration. Rubber materials are used in various water filtration systems. For example, rubber membranes are used in reverse osmosis systems to filter out contaminants from water, providing a reliable and durable filtration method. Wastewater treatment. In wastewater treatment plants, rubber seals and gaskets are used in tanks and pipes to ensure that there is no leakage or contamination. Specialized rubber compounds are used to resist corrosion from chemicals and pollutants found in wastewater. Pollution control. Rubber products such as seals and gaskets are used in pollution control systems, particularly in industries that generate harmful emissions or waste gases. These components help ensure that systems remain airtight and functional. 26. Future challenges and innovations. End-of-life rubber disposal. One of the biggest challenges facing the rubber industry is dealing with the disposal of end-of-life rubber products, particularly tires. While some recycling methods exist, there is still a significant gap in terms of developing cost-effective large-scale recycling technologies. This is an area of ongoing research, improving durability and longevity. Researchers continue to seek ways to make rubber products last longer, especially for industries like automotive and heavy machinery, where wear and tear can significantly impact performance. Advancements in cross-linking techniques, material formulations, and coatings are helping to extend the life of rubber products, reducing environmental footprint. The rubber manufacturing process, especially in synthetic rubber production, is energy-intensive and reliant on petrochemical-based materials. There is a growing push to reduce this environmental impact through renewable energy sources, green chemistry, and sustainable sourcing of materials. 27. Rubber in the energy industry. Rubber plays a significant role in the energy sector, particularly in applications that require high durability and resistance to extreme conditions. Oil and gas industry. In oil rigs, refineries, and pipelines, rubber is used in seals, gaskets, and hoses due to its resistance to petroleum-based products, heat, and pressure. Specialized elastomers, such as hydrogenated nitrile rubber, HNBR, are used in environments with high oil and gas exposure. Seals and drilling equipment. Rubber seals are essential in preventing leaks and maintaining pressure in drilling operations. These seals must withstand exposure to chemicals, high pressure, and elevated temperatures. These rubber products need to be durable, flexible, and resistant to corrosion. Energy storage. In energy storage systems, particularly in batteries and capacitors, rubber-based materials are used for insulation, seals, and protection. Some newer energy storage technologies, such as supercapacitors, rely on rubber-like polymers for flexibility and to protect sensitive internal components. Renewable energy systems. Rubber components are used in wind turbines, solar panels, and geothermal systems. For example, rubber seals and gaskets are used in solar panel installations to prevent water leakage and ensure weatherproofing. Wind turbine blades. Flexible rubber-like materials are used in wind turbine blades to reduce vibration, increase efficiency, and improve resistance to extreme weather conditions. 28. Rubber in the construction industry. Rubber products are extensively used in construction, where they offer sound insulation, vibration damping, and sealing functions. Building seals. Rubber seals and gaskets are used to prevent water ingress, maintain temperature control, and reduce noise in windows, doors, and roofing systems. EPDM ethylene, propylene diene monomer, rubber, for example, is widely used in roofing due to its superior weather and UV resistance. Expansion joints. In concrete and steel structures, rubber expansion joints are used to accommodate movement due to temperature fluctuations or structural settling. These joints prevent cracks in buildings and roads by absorbing stress and motion. Soundproofing and vibration isolation. Rubber materials are used in flooring and wall systems to reduce noise and vibrations in buildings. In particular, rubber underlayments are often placed under floors to absorb sound, especially in multi-story buildings and high-rise apartments. Rubber in roads. Rubber modified asphalt RMA, made by incorporating crumb rubber from recycled tires into asphalt, is increasingly used in road construction. This combination improves the durability of roads, provides better traction, and reduces noise, while also promoting recycling of used tires. 29. Rubber in military and defense applications. The defense industry uses specialized rubber materials for high-performance extreme condition applications. Sealing and insulation. Rubber seals and gaskets are critical components in military equipment, such as armored vehicles, submarines, and aircraft, ensuring that sensitive electronics and engines are protected from contaminants, moisture, and pressure. Protective coatings. Rubber-based coatings are used to protect military vehicles, ships, and aircraft from corrosion, wear, and damage. These coatings provide a durable layer of protection against the elements and improve the lifespan of defense equipment. Ballistic protection. Rubber materials are sometimes incorporated into composite materials used in body armor and vehicle armor due to their shock-absorbing properties, providing extra protection against impacts and projectiles. Rubber in camouflage. In the field of camouflage, rubberized coatings can be applied to military vehicles and equipment to reduce their visibility and provide thermal insulation. Rubber-based camouflage nets are also used to hide equipment or personnel from enemy surveillance. 30. Rubber in the fashion industry. Rubber footwear. In addition to its widespread use in industrial footwear, rubber is also used in high-fashion items, particularly in rain boots, sneakers, and sandals. Designers incorporate rubber into footwear for both aesthetic appeal and functionality, offering water resistance, flexibility, and comfort. Accessories. Rubber bands, straps, and other accessories are becoming more common in fashion collections. Rubber jewelry, like bracelets and rings, is popular in trendy designs, especially in sportswear and urban fashion. Sustainable fashion. Many brands are now using recycled rubber in clothing and accessories as part of their commitment to sustainability. Rubber made from upcycled tires or industrial waste is being used in products such as bags, belts, and footwear. 31. Rubber in the food industry. Food handling equipment. Rubber materials are widely used in the food processing industry to handle, store, and package food products safely. Rubber conveyor belts, seals, and gaskets are designed to withstand the rigors of food production environments. Food-grade rubber. Rubber that comes into direct contact with food must meet strict regulatory standards for safety and hygiene. Food-grade rubber materials are made with additives that prevent contamination, and they are designed to be easy to clean and sanitize. Seals and packaging. Rubber seals are used in food packaging to create airtight, leak-proof containers that extend shelf life. Food processing machinery. Rubber hoses and gaskets are essential in machinery used to process dairy, meats, and other food products, ensuring sanitary conditions and preventing contamination.